All right, everyone. We'll get started here. Again, my name is Aaron Oslin. I'm with Forberg Scientific. I'm the branch manager of our office here in Wisconsin. First of all, thank you all for taking some time to join us today for our webinar here. We'll be joined by Matt Kelsey from Endress+Hauser to give a presentation about non-contact level measurement in a few moments. Before we get to that, I just want to go over a couple of housekeeping items. And then I'm going to say a few words about Forberg Scientific, and then we'll turn it over to Matt. So first of all, this webinar is being recorded. So I know there were some people that reached out and said they weren't able to join today. So it's a new system for us. So hopefully we get it all worked out, and we're able to capture a recording of this and get it out to anybody. So if any of your colleagues or people you know weren't able to join us, feel free to have them reach out to their Forberg contact, and we will get a recording out to them, or at worst, the actual content of the slide deck. As far as the flow of the presentation, I'll be talking for a few minutes, and then Matt Kelsey will be joining us. There is a Q&A box that I will be monitoring. So if you've got questions in there, please feel free to type them. I will be asking, interjecting with those questions for Matt. It is anonymous, but if you guys do log in or want to give your name, that's great. Otherwise, we can keep the questions anonymous. And then we'll leave some time at the end after the presentation if there's some questions, but feel free to ask them at any point in time. So I'm going to switch over to some collateral, and then we'll get going. Okay, well, hopefully, and if you can't see this or something didn't come up, hopefully everyone can see a presentation that's up now. Feel free to type a question or an issue if you can't see it. But again, welcome everyone to it's actually our second virtual lunch and learn here that we've done. We did one a couple weeks ago about regarding pH probes, cleaning, and calibrating those. Today we're going to be talking a little bit about level measurement, non-contact level measurement. Again, I want to just say a few words about Forberg Scientific before we turn it over to Matt. Forberg's been around for almost 50 years as a distributor for manufacturer and manufacturer's rep. We've been in Wisconsin for almost 5 years now, serving a number of customers, a number of you who have joined this call today. Currently, we have 9 locations right now, 2 stocking warehouses. You can get an idea of where we are. Like I said, I manage our operation out of our Menominee Falls office. My team covers most of Wisconsin and the Upper Peninsula of Michigan, but you can see, we're pretty broad breadth of reach as far as our territory. We cover many major markets: pharmaceutical, food and beverage, oil and gas, chemical, life sciences, with a variety of products, both distributed products and represented products like Endress+Hauser, with whom Matt Kelsey is with, that you'll talk to in a few moments. Again, just some additional markets we're in: drinking water, power gen, wastewater, all kinds of different manufacturing, and then automotive. We are based in Detroit, Michigan, so obviously the automotive industry is kind of at our core. We also have a very vibrant website, forberg.com. I don't know if a lot of people have visited that, but we do have online purchasing capabilities for our distributor products, such as valves, fittings, tubing, hoses, things like that. So I encourage you to visit forberg.com. You can sign up, get your pricing right online, purchase right online, and it's a very convenient tool. So with regards to Endress+Hauser, like I mentioned before, Matt from Endress+Hauser will be speaking in a few minutes. Forberg's been an Endress+Hauser representative for about 15 years. We're one of the 3 largest representatives in their network, so we have a lot of experience with their products, with their people. We are a authorized service provider for Endress+Hauser, so startup services, commissioning, calibration, our technicians are able to perform all of those services. You can see on the side where we currently have Endress+Hauser, Michigan, Ohio, Wisconsin, parts of Pennsylvania, and West Virginia. We have process sales and service staffs in all of our offices who are factory trained application experts. I'm sure many of you have worked with your outside salespeople, but probably also our inside sales team who are very knowledgeable to help, not just with the Endress+Hauser product, but all of our product lines to help find the right fit for your solutions. Just a note on some other product lines that we represent. We actually began as a Parker Hannifin distributor in 1971. So that is a lot of our inventory. So valves, fittings, tubing. We're the Samson Control representative, as well as Draeger fixed gas detection. We're the largest Burkert distributor in the country. So we've got a really broad basket of products that we hope to be able to help you guys out with sometime. But today, really, we're going to focus on Endress+Hauser. Like I said, we have Matt Kelsey, who is a regional product manager for their level group, with us today, and he is going to talk about selecting the right radar frequency, is kind of his title here, but really choosing the right non-contact radar technology or ultrasonic, depending on the application. So I will turn it over to Matt right now to go ahead. And again, if you've got questions, please type them in the Q&A and we will do our best to get them all answered. So Matt, floor is yours.
Awesome. Thanks, Aaron. And yeah, I appreciate everybody taking some time out of their day to join us here. Like Aaron said, my name's Matt. I'm the product business manager, specifically looking at level products here for Endress+Hauser. Cover the Midwest region, which includes all of Forburg territory, as well as up into the Dakotas and all the way down through West Virginia. So I call this the art of selecting the correct radar frequency, as there's really no perfect formula for selection of a radar, or even more generically, a level device. So you'll probably hear me say it multiple times throughout the presentation, but there's unfortunately no one-size-fits-all approach for level measurement. In many cases, there's 2, 3, maybe 4 different technologies or styles of probe that might work for the application, but then it must be determined which one's going to perform best. So that's kind of where that art portion comes into it. So if you want to go ahead and go to the next one.
Yep.
Just a little bit about me. I've been with Endress+Hauser coming up on 5 years now. So I started out in applications engineering, pretty much always focusing on level products. So my whole 5 years here, I've done pretty much nothing but level. So it's been about 2.5 years in application engineering and about 2.5 years now in my current role. Graduated with a mechanical engineering degree from Rose-Hulman Institute of Technology. It's a small engineering school on the west side of Indiana. A lot of people haven't heard of it, but that's okay. Just a little bit about me. I love to travel, hike, really do anything outdoors. This picture is a photo from a recent trip my wife and I were able to take. Luckily, actually, we were very fortunate to be able to go to Thailand just in February, just before everything kind of got closed down for COVID. So pretty much about the time we got back is when things started shutting down. So yeah, we were very fortunate to be able to go on that trip. Okay. So I'll cover just a little bit of theory. I don't want to spend too much time on this, but I do think it's important to just make sure everybody's got a base understanding of how they work. So both radar and ultrasonic measurement is based off of what we call the time of flight principle. A signal is emitted from the device, travels down to the product surface, where it's then reflected back up. What we're measuring is actually the time that it takes that signal to go down and back, which is proportional to the level in the tank or whatever you're measuring. So the difference between a radar and an ultrasonic here is the type of signal that gets sent out. So a radar is an electromagnetic wave, whereas an ultrasonic is actually mechanical sound wave. So really the only difference in this equation that you see here is the C. For a radar device, that C is the speed of light, is what the radar signal travels through air. Whereas for an ultrasonic, it's the speed of sound that the signal travels through air. Go on to the next. So the ultrasonic will reflect off the surface of the product based off of a difference in density from air to the product. So air being a low density, your product having a higher density. If you have a very highly dense product, you'll get a big signal reflection back. A little bit different on this radar side is that it reflects based off of the dielectric constant of the material. So you might see different terms or signal symbols for this. So in this chart, you see epsilon, you might see DC value, DK value, dielectric, lots of different things you might see. They're all pretty much the same. So when we look at this, air is kind of a baseline dielectric. It has a dielectric of 1. Water is one of the highest dielectric values at around 80. So generally, liquids have higher dielectrics than solids. Anything above 10 or so is considered very hot dielectric and is a very good candidate to use a radar device for. In the range of, say, 4 to 10 is kind of that mid-range, still a good candidate for radar, definitely doable. Maybe a couple things you want to take a look at just to make sure it's a good application. And the measurement starts to become a little more difficult, not impossible, but more difficult around a dielectric of 2. So at that point, you kind of need to look at the application as a whole and make sure the installation is going to be correct and that process conditions will allow for a good, reliable measurement. Okay. So on the left here, you'll see what a typical signal might look like for a radar device. So again, this is just a simple tank where we might be measuring water, which again has very high dielectric. So up at the top near the process connection, you get a big peak, and that's your signal launching out. As it travels down, hits the water, you get a nice big signal reflection. Almost all of that energy from the radar is reflected back up to the unit, and you just have this one peak that the radar has to pick out as a level, a very easy application. Next. So on the right, you can now see an ultrasonic device, and for water, it looks very, very similar. The reason is that air and water have a big density difference. So you get that same type of signal launch, the signal travels down, and you get a nice big reflection off the surface of the water. It's very easy for that ultrasonic device to pick out the level. So go to the next slide and look at what signals look like in a lower dielectric, something like an oil-based product. For a radar, you have that same signal launch, it travels down. Now you see you get a much smaller reflection off the surface of that oil because of the lower dielectric. And then actually some of that energy is reflected, but much of it actually continues to travel down through the oil. And you see at the bottom left of the screen another peak. That peak is actually the tank bottom, but you see it's shifted below where the actual bottom of the tank is. And that's due to the fact that that radar signal is traveling actually slower through the oil than it is through the air, so you get what we see in that shift. That's part of why measuring in a lower dielectric media is a little more difficult than a high dielectric. You often see multiple peaks. Things are sometimes shifted from where they actually are in the tank. So it's just a little more signal processing that the radar has to do. Next, you look at an ultrasonic in the same application, and this one actually looks very similar to what it does in water. And again, that's because we're looking at a difference in density, which air and oil still have a plenty big density difference, that all of that signal is reflected back up to the unit. It becomes very easy to measure. So on the next, we'll look at kind of when you might use a radar versus an ultrasonic. So if you start on the left looking at maybe what's good about a radar, one, it's less influenced by environmental factors such as gas composition, pressure, or temperature. Like I said, with an ultrasonic being a mechanical wave, it's, I guess, calibrated to use in air. So if you've got a nitrogen blanket, say, on top of your tank, an ultrasonic's not a good candidate because that signal is going to travel a different speed in that gas composition than it would in air. Radars are more accurate, and they often have much longer measuring ranges as well, so they cover a wider basket of applications. Many of the new technological advances are going into radars, so you'll see a lot more features and benefits, a lot of advancements in radar technology as opposed to ultrasonic in our basket as well as others. And I would say for radar devices, we'll cover most applications. Probably in the like 85% range of non-contacting devices are probably going to be radar devices, especially in like process tank type applications. So anything where you're enclosed in a tank is especially well suited for a radar device. Ultrasonic does have its benefits and its place for sure. So for one, it's quite a bit faster response time than a radar device. So if you have something, especially in a short range, that's changing quite rapidly, and ultrasonic is a great choice for that. The other place where it really shines is in flow type applications, where we're using a level measurement to then calculate a flow. So most notably open channel flow happens a lot in the municipal market. Ultrasonics are great for that application. The other is solids flow on a belt. So if you've got any sort of solid material flowing along a conveyor belt or in a screw conveyor, auger, anything like that, an ultrasonic is better suited there as well. All right, going to the next. So from here on, I'm mostly going to cover radar devices. That's kind of the bulk of the presentation, I think, where we can get the most out of. So I want to take just a second and kind of look at what's available on the market today. So generally, they'll fall within 4 different frequency bands. So guided radar operates around 1 gigahertz in the L band. We have low frequency free space radars that operate in the C band, mid-frequency radars that operate in the K band, and then newer high-frequency radars operate in the W band. So radars that operate within the same frequency band, whether, if you're looking at the K band, whether that's 18 or 27 gigahertz, those radars are going to have very similar characteristics. So different manufacturers might use a slightly different frequency within that band, but for the most part, if it's in the same frequency band, like a K band, the characteristics will be fairly similar. However, as you move from one band of radar to the next, you see drastic differences in the characteristics, which is what we're going to cover today. So for the last 15 years or so, K-band radar was considered high frequency. That 26 gigahertz was high frequency. It was the highest available on the market, and it was used for nearly all applications. However, within the last couple of years, W-band radars have become available and are now what's considered high frequency and are becoming more and more popular. So we'll again kind of cover the differences between all of these frequency bands and then when you might use one versus another. Okay. So it's important to note that there are different classes of radar based on the application and customer needs. So if you go to the next, this could range anywhere from a very economical radar, something like a little battery powered unit that's meant for remote monitoring, where you're going to get lower accuracy, but it comes at a much lower price. If you go to the next, you see a process grade radar, which is what is most common in most industries that we cover. So if you're looking at a storage tank or a reactor or something like that, this is kind of in that range that you're looking at. So you get good accuracy, mid-level price. Go to the next is the highest level of accuracy, or tank gauging style radars, where you've got a large diameter tank, so a small change in level has a big impact on volume. You need that highest level of accuracy. So again, just wanted to point this out and also let you guys know that Endress+Hauser can cover all of these different classes and styles of radars, making sure that we're meeting the needs for your application, whatever that may be.
And Matt, before we move on, we had a question come in from one of the attendees. The question is, we have had problems with radar measuring animal byproducts. How do you measure the dielectric constant of a specific liquid?
Sure. So if it's a fairly typical liquid, I would say animal byproduct is not that. But if you've got a more common liquid, Endress+Hauser does have a large database that we can look up dielectric constants. So we've done a lot of testing and just have a database of recorded liquids and solids. If you've got something a little bit unique, we do have portable dielectric testers that are available. It's just a little canister that you fill up with a sample of the product, and it will get you an idea of what that dielectric is. So if it's something that you've had problems with and you think dielectric may be the reason why, get with your local Fordberg representative. They can reach out to me, or you can reach out to me. We'll set something up and see if we can't get it tested for you.
All right, thanks, Matt. All right, you ready to move forward?
Yep.
All right, great.
Okay, so why do we have all of these different options? Like I said before, when it comes to level measurement, especially radar, there's no silver bullet, no one size fits all. I really wish there was. It would make my job a lot easier if I could just tell you, here's the device, use it for every application, and you're going to be all set. It's just unfortunately not the case. So really each application presents its own different difficulties. And that's why we keep all these different styles around, so that we make sure that we can tackle any application that you bring to us. So when you get questions from myself or from your Fordberg rep asking about process conditions, tank heights, what product you're trying to measure, we're really just trying to narrow down the selection so that we can figure out what's going to work best. This slide just gives a quick overview, a couple bullet points each of the frequencies and where it might have its advantages, but I'll cover them in a little more detail later. However, from this point on, I'm going to focus mostly on non-contacting, but did want to point out the fact that we do have guided radar as well, and just a couple of places where it really shines. So I typically say if you're able to have a probe in contact with the process, you're going to have a more reliable measurement. Really, anytime you can have that, you're just constraining that signal around the probe, and it's going to be a little bit more reliable. That's often not possible due to mechanical forces. Maybe there's an agitator, or maybe there's just the desire to keep everything out of the process if you can. A couple places where you can use a guided radar to make measurements where non-contacting just won't work. The first is an interface measurement. So if you've got a separation type process, where you've got maybe the most typical is an oil layer on top of water, with a guided radar, we're able to measure both that oil level and the water level all in one device. The other is if you've got very high pressure and temperature applications, most notably would be a steam boiler. We have what we call gas phase compensation available on radar devices. It just makes them much more accurate in those high pressure applications, whereas a non-contacting radar would see a large degree of error. We can go to the next.
Okay.
These are the four main points that I'm going to cover today, and really what characterizes a radar based on the frequency. So it's going to be beam angle, the radar design, the accuracy, and then the measuring range. Next. So your beam angle of a radar is influenced by two factors, and you'll see this in the next slide in pictures, but I wanted to start with the graph here. So the first is your antenna size. And when I say antenna size, what I mean is the diameter of that horn. So the bigger your antenna, the smaller your beam angle is going to be. However, with a bigger antenna, that means you've got to have a bigger opening in your tank. So if you've got a 4-inch antenna, typically you need a 4-inch nozzle in your tank to be able to install it. So if you look at the chart, let's just focus on that middle column of 26 gigahertz. As you move down that column, that's increasing your antenna size. You see that your beam angle starts to shrink. So that's what I mean when I say bigger antenna is a smaller beam angle. The other factor that influences the beam angle is the frequency. So as we increase frequency, we have a smaller beam angle even at the same size of antenna. So now if you look, instead of down the column, let's focus on, say, the 2-inch size antenna and move left to right. You see on the low frequency 6 gigahertz, we actually don't even offer a 2-inch antenna. It would just not really be well suited for really any type of application, so we don't offer it at all. On the 26 gigahertz, you have an 18-degree beam angle, and if you jump up to 80 gigahertz, you shrink that down to the 6 to 7 degree range. So quite a big difference keeping the same size of antenna, just moving up to the next frequency band. Going to the next. So here we'll just show this pretty much the same thing, just in picture form. I like pictures personally to help me learn, so we'll put this up here for you guys. So the first shows a 6 gigahertz low frequency radar, a big 6-inch antenna. So you can see that antenna's got a big diameter. That means you've got a big opening in that tank, but still a big beam angle. You can see that signal in yellow there. It's probably going to hit the tuning fork or switch you've got put into the side of your tank. You're going to see those heating coils or baffle plates down in the bottom of the tank as well. So that's not to say that this couldn't be used, but the setup becomes a little bit more difficult. You've got to make sure you do a good mapping of the tank to ignore all of these obstacles where you're going to see reflections, but those aren't the level. So again, can be done, just a little bit more on the setup. If you go to the next and look at what a 26 gigahertz radar might look like in this application, here we can shrink it down to a 3-inch antenna. So we cut that size in half, means your tank opening is much smaller, and we drastically reduce that beam angle. So now maybe we don't have any influence or signal return from the tuning fork or the switch up in the top of the tank, but as that signal spreads out as it goes down into the bottom of the tank, maybe you do still get a little reflection off of your heating coils or baffle plates. So again, a good mapping of the tank is still probably needed here. Going to the next now, with an 80 gigahertz radar, we keep that same 3-inch size antenna, but now we've shrunk the beam angle down to 3 degrees. So beam angle, I'll say, is probably the biggest thing, or the biggest benefit to a higher frequency radar. Typically, a smaller beam angle is desirable, and that's because it makes commissioning much, much easier. You can see in the picture, if that signal's not hitting any of the obstacles in your tank, that means there's no false reflections coming back. You don't have to program the radar to ignore them. So the other thing it allows, that I'll show in a little bit, is much smaller process connections, as you've seen, because we can maintain smaller beam angles. And it also allows us to mount in much taller nozzles because of that small beam angle. There you go to the next. So like I said, typically a small beam angle is desirable. However, there is a little bit of a drawback, and the main one is turbulent surfaces. So on the picture here, we'll pretend that this little plastic wavy piece is a product surface. So maybe you've got a small mixing agitator in a tank, or maybe you're filling from above. It's creating some turbulence on the surface. We focus on first the basketball. That would be representative of a low frequency unit. So a big beam angle is going to give you a big footprint on the product surface. The benefit here is that big footprint. If you imagine dropping that basketball from above that wavy plastic, like your radar signal is going to come down, nearly every time that basketball is going to bounce straight back up to the radar device, meaning that almost all of your radar signal is going to come straight back up to the radar, meaning you've got a nice good reflection even with a turbulent surface. If you move over to the pink ball now, that's a little bit smaller, more representative of a mid-range frequency unit. So again, you drop that ball from above, probably 9 out of 10 times, it's going to come straight back up and you're going to get a good signal return. However, now if you look at the tennis balls, that's representative of an 80 gigahertz, so really small beam angle. And if you drop that tennis ball from above, maybe only half the time it's going to come straight back up. So sometimes you get a good signal return, sometimes you don't. So really choosing a frequency and a beam angle is really a balance, right? Because you don't always want that biggest footprint, because maybe you have a lot of obstacles in your tank, and it might be difficult to program the unit to ignore some of those. So a lot of times in turbulent applications, a 26 gigahertz radar is the perfect kind of in between. And again, this is not kind of like a hard and fast, you can't ever use an 80 gigahertz radar in an application where there's a little bit of surface turbulence. It's just another factor that plays into the selection. Okay, can go to the next. So when we look at radar design, the biggest thing that's influenced by the frequency is the size, the physical size of the unit. So again, higher frequencies are going to allow for very similar performance, but with smaller process connections. So looking left to right, an 80 gigahertz radar for the first time allows us to get down to a 3/4 inch NPT non-contacting radar device. Previously, 1.5 inch was as small as we could go. So this is great, especially in retrofit type applications where maybe you had a capacitance probe or a guided radar installed before. All you have available is a 3/4 inch NPT. Now, if the application allows, we can put a non-contact radar in there as well. This is also good in small vessels. Small vessels typically are a little crammed on top of them, so being able to put a small process connection is very beneficial. If you kind of compare the two on the right now, what I'm looking at here is we've got similar beam angles, so a 6 degree with the 80 gigahertz unit and an 8 degree with the 26. However, you can see the drastic difference in the size of the connection. So with high frequency, we can do this with an 1.5 inch NPT, very small unit. But with the 26 gigahertz, it's going to take a 4-inch flange and a 4-inch antenna to get that similar performance in terms of beam angle. So these devices become much more manageable in terms of size, makes the installation a little easier. On to the next. So this point, in terms of the antenna shape and the design, isn't necessarily directly related to frequency, but it is an important conversation nonetheless, so I wanted to cover it for just a second. So there are really two main types of radar antennas. Those that have the big metal horns, like on the left, that protrude down from the process connection, and those that are more of a flush mount design. So this flush mount PTFE Teflon style design is better with handling condensation and buildup. So this shape will collect condensation on it, water droplets will form, but because of that kind of half golf ball shape, they tend to collect up on that and then just drip right off the end, which doesn't really have any effect on the radar. However, if you look at the big horn style radar, those also collect water droplets up on the inside of that big horn, and those water droplets will actually absorb a lot of the signal that's sent out from the radar, making the measurement much more difficult. The one downside, I'll say, to having this PTFE style radar is that we are limited by temperature. So that's roughly 400 degrees F, just a little bit below. Whereas with the horn style radar, we do have versions that allow us to reach much higher temperatures. Okay, next. So accuracy is also affected or influenced by the frequency range. So when you increase the frequency, you're kind of just focusing all of that energy into a more narrow band, which allows us to achieve higher accuracy. So looking at this chart on the right, let's first focus on the blue line. So this blue line is representative of what a typical signal might look like for a low frequency radar device. Where those arrows are pointing is kind of where it's saying the level is at. And you can see the reflection you get from a 6 gigahertz radar is a very broad peak. So now the radar has to take this broad peak and pick a point along the peak. So your left to right x-axis is your distance away from the unit. The device now has to pick a point along that peak that the actual level is at. That's where you end up getting the 6 to 10 millimeter accuracy with a 6 gigahertz radar. It's just because you've got this broad peak and the radar is more or less just picking a point along that peak. If you look at the red line, it's more representative of a 26 gigahertz radar. So you can see the signal return is a much sharper peak. That just leaves less room for error for the radar to pick the wrong point along that peak. That's how you can get down into the 2 or 3 millimeter accuracy range. I unfortunately don't have an overlay of an 80 gigahertz radar, but you can imagine it's just an even sharper peak than that red line. And again, that allows us to increase that accuracy to 0.5 millimeter to about 2. Okay, we can go to the next. The other notable point is measurement in the bottom part of a vessel. So again, with those sharper peaks, it allows us to measure closer to the bottom of the tank. You saw I described at the beginning during the theory how the radar in a low dielectric will actually continue to travel through that media, and you get a reflection off that tank bottom. The left is what you might see with the level close to the tank bottom with a mid or low frequency radar unit. So you can see you get a little bit of a hump there on the left where the level might be, but then you get a really big reflection off of the tank bottom, and those two peaks are kind of merged together. There's no way for the radar to distinguish them, so it just locks onto the tank bottom. What that means is that a radar in that frequency range will read down to maybe about 6 inches, 8 inches to the tank bottom with a low dielectric, but then anything lower than that, and it's just going to lock onto that tank bottom and read 0. So you lose just a little bit of the lower measuring range. If you look on the right though, on a high frequency radar, because that signal is more focused, we get 2 distinguishable peaks even at lower levels in a low dielectric. So again, this allows us to kind of increase our accuracy and increase the usable range of the device, especially down low in the tank. Okay, next. So if we look at measuring range, this is kind of along the same lines as the accuracy, but again, with higher frequencies, you're focusing that energy, which allows us to also measure further ranges. So higher frequencies, longer measuring ranges. In liquids, we can measure with high frequency up to something like 260 feet. I don't know of a tank that's that tall that holds liquids, but if there was one, we could probably measure it. In solids, it's even further than that. It's 400 plus feet. So I don't think there's a silo out there that is too tall for us to measure. However, it's also important to note that frequency is not the only thing that affects it. The dielectric constant, like we talked about earlier, and also process conditions have an impact on this. So go to the next. This shows the influence of dielectric. So down in the bottom left, you see kind of what those A, B, C, and D ranges are. And then in the chart, you can see what you're looking at here is the number that's in parentheses. So that's the measuring range in feet. So in a storage vessel where there's not much going on, no turbulence or anything, with that A group, very low dielectric, we are able to measure 32 feet away. But if you go up to a high dielectric, so if you had water in that same tank, now we're able to measure 131 feet away. So again, that's just because that higher dielectric is going to reflect more of that radar signal back up. Go next. We look at what do process conditions, or what effect do process conditions have on the measuring range. So now we're kind of comparing the storage vessel to the agitated vessel. So this is the same style of radar, same size of horn. Now you can see because of that turbulent surface, we're actually no longer to measure at all that lowest dielectric range. So we actually only start with the B, and you can see if you look at even water in an agitated vessel, we're able to measure about 32 feet. However, in just a storage vessel, again, it's 131 feet. So you can see what a turbulent surface does to your measuring range as well. Next. Okay, so this high frequency, it seems great. Are there any drawbacks? Yeah, there are a few. The first one, and probably the biggest, we kind of talked about already, and that's turbulent surfaces. Again, we can use high frequency radars in these applications. You just need to look at it on a whole, look at the dielectric, look at the installation conditions, and just make sure that it's a good fit. The use of high frequency devices in stilling wells or bridle assemblies is not recommended. So in this case, actually lower frequencies or guided wave is the best. will perform better here. So just based on our testing, these high frequency radars have a lot of signal noise when installed in this way, so we don't recommend it. You've also got to be careful with certain chemicals and frequency. So things such as methyl chloride, acetone, MEK, other solvents in that ketone family will not work with high frequency 80 gigahertz radar. So this is due to a phenomenon where at that frequency range, the vapors of those solvents actually are excited. They have a resonant frequency around 80 gigahertz. So when we send out that signal, the vapors actually just absorb all of that signal and receive no signal return. So if you have these chemicals as part of your process, or you're just measuring one of those chemicals, you will not want to use a high frequency radar. A lower frequency, 26 gigahertz or 6 gigahertz, will have no problem. You just can't use the high frequency. Similar phenomena is seen with the K-band or 26 gigahertz radar and ammonia. Same lines there. We can use a high frequency in ammonia or a low frequency, just not that middle band. The last point is that high frequency radar does have just a slightly slower response time than lower frequency ranges. And that's just because a little bit of extra signal processing. So it's not a lot, but if you do have a small vessel that fills and empties very quickly, you're probably going to be better off with a lower frequency band. Okay. All right, so let's look at when you might choose one over the other. And what we're looking at here is kind of a good, better, best scenario. So we'll have actually a red box if it's not recommended, a yellow box if it could work, but there's some considerations. We'll have a light green for a good selection and a dark green for a best. So this chart first covers mostly installation and mounting conditions. We'll cover process conditions next. So for storage tanks, if you click, really just about any device is going to work in a storage tank. So these are simple applications where you don't have an agitator. There's not a whole lot going on in the vessel. We list the higher frequencies as better just because of the smaller beam angles. There's less commissioning that you have to do from interference from the sidewall or anything like that. Next, in process tanks, again, your higher frequencies are probably going to be better there. Mainly the consideration here is in process tanks, you're likely to have a lot more obstacles in that tank. So having a small beam angle is going to make that commissioning a lot easier. In small tanks, low frequency is actually not recommended in very small tanks. High frequency will perform much better there in short ranges. And also it doesn't hurt that the high frequency has smaller process connections available, which leads right into the next one. So again, as you increase your frequency, your process connections get smaller and smaller while being able to maintain the same type of beam angle, same accuracy. For hygienic applications, this is really more dependent on radar design, not necessarily the frequency. However, in our C-band portfolio, we don't have any hygienic designs, which is why you see that listed as red. In both the K-band and W-band, we do have hygienic designs available. Some are and some aren't, so that's why it's listed as kind of that light green, but we do have solutions available. For nozzle installation, your higher frequency is going to be better suited for this. So we can measure through tall, narrow nozzles without the need for any antenna extension. So in the past, before high frequency radar, we could measure through tall nozzles, but we had to use what's called an antenna extension. So more or less it puts a rod between the process connection and that horn style antenna, and it just extends it down into the tank, as it's ideal to have that horn extending just down into the vessel itself. So it was possible, but it led to additional cost to be able to manufacture. And now you've got this really big antenna extension on the end of a radar that's difficult to mount. Next is ball valve mounting. So this kind of goes along the same lines as nozzle installation, but with higher frequency radars in that W band, we are able to very easily mount right on top of a full port ball valve and measure through it down into the tank and get the level. So what that allows you to do is if you've got a application or a process that's critical that you don't want to ever shut down, you can isolate that radar with a ball valve. That way you can close off that ball valve, do any maintenance, repair, swap out that radar device without having to shut down your process. Installation in a bypass or steering well. Talked about this, lower frequencies are going to be better here, but the best is actually a guided wave radar. And with many obstacles in your tank, you're going to be better off with a high frequency radar, and that's just due to the fact that you've got a smaller beam angle, which means less commissioning work for you. So next we'll look at, again, application influences. So with condensation or buildup, we talked a little bit about this on the antenna design. So we talked about kind of that drip off or flush mount style device that's going to handle it better. But what I didn't mention is that lower frequencies actually perform also well in condensation and buildup. And that's just because that low frequency travels through that condensation or buildup better than a high frequency does. So I always relate this to like a foghorn. So a foghorn is a very low frequency and it penetrates through that fog, or what you could relate to steam or condensation, very well. So lower frequencies are less affected, but all of the lower frequencies have that big horn style. So typically in those applications, I would prefer to go to a higher frequency that has the flush mount style design. For low dielectrics, a higher frequency, you're going to get a longer measuring range and better performance. So possible to measure in all of our frequency bands, best to do with a high frequency. Foam is a fairly difficult topic, as unfortunately all foam type applications are different. So what I've put on this chart is assuming that you want to ignore the foam and measure the liquid level underneath. In that case, similar to condensation, your low frequency is going to be better there because that lower frequency will penetrate through that foam and get a bigger signal reflection off the surface of the product. However, if you were actually wanting to measure the top layer of the foam, you'd be better off to go the opposite way and use a high frequency device. If you've got a process that changes level very fast, again, your lower frequency is going to be better there, as the high frequency has a little bit slower reaction time. But if you've got a very small vessel, something like a little filling bowl, if you're in the food and bev industry, a capacitance probe is going to be your best bet. So that's the absolute fastest reaction time you can get out of a level device. And again, part of the reason why we keep around all these different technologies and styles. Turbulent surfaces we discussed and talked about how your lower frequencies will typically work better there, as kind of gives you that average level of that turbulent surface with most of your signal coming back up to the radar. When you look at aggressive media, so if you're looking at chemical compatibility, this really depends on the design of the radar and the materials used. So I've got the K-band and W-band as green here, and that's because we have on those frequency ranges, we have available that PTFE style version. So PTFE Teflon is your only wetted part with that design, and it's a very inert material compatible with many, many products. On our other styles, we do have alloys and different exotic materials available for those applications, but that generally comes with a higher price tag. So if you can use Teflon in the application, generally that's the way we'll go. high pressure and high temperature was discussed just a little bit. So again, on our lower frequencies, we have the ability to reach higher pressures and temperatures up exceeding 750 degrees, whereas on the W-band radars, all of those radars are got more Teflon style, so we're limited to 392 degrees F. And again, just be careful if you're working, especially with solvents and high frequency. So just look at this absorption phenomena in the lower frequency bands or guided radar. There's no known issues with any chemicals or solvents out there, so you're good to go. If you're working with ammonia, just avoid that 26 gigahertz. And if you're working with solvents, I would say it's best to contact Forberg or Endress+Hauser to get a recommendation and make sure that what you're proposing is going to work well. All right, that's all I've got for today. I really, again, appreciate everybody taking some time. You see my contact information here. If you have any outstanding questions or applications that you want to talk about more in depth on a personal level, feel free to reach out to myself, reach out to your Forberg representative. We'd be happy to set up some time and talk through anything with you. So again, thanks to Forberg. Aaron, I guess if there's any other questions out there.
Yeah, thank you, Matt, for spending some time with us. I'll leave Matt's contact information up there. If anybody has questions, feel free to put them in the Q&A at this point. We'll try to get them answered right now. Otherwise, Matt's contact information, and feel free to reach out to him or your Forberg contact. So we'll stay on for a few minutes, and if you have to drop off, again, thank you for attending, and please let us know if there's anything we can do for you. All right, we do have a question, Matt, for everyone still on there. It asks, would you review what you stated about oils at the beginning? I'm guessing, and Dave, you can type in some more information. If you're referring to, I think he's maybe talking about the difference, the dielectric difference versus the density difference, perhaps.
Sure. Yeah. So really, what we're looking at is a difference in either dielectric or density from air to the product you're measuring. So if you look at a radar device, the difference in dielectric from air 1 to water 80 is a very large difference in dielectric, meaning that you're going to get almost all of that signal reflected off the surface, come back to the radar, very easy to measure. If you look at oil, though, oil with a dielectric of roughly 2, that difference between 1 and 2 is now much smaller, so only a little bit of that signal is reflected, and some of it continues to travel through the product. However, if you look at ultrasonic, the density of oil and water are very similar and are very different from that of air. So in that case, you actually, almost all of your signal gets reflected on an ultrasonic device from oil or water, making it fairly easy to measure.
Okay, thanks, Matt. Yeah, and I sent Dave a quick chatter note just to see if, oh, now he's got it, so great. Okay. Good. Well, if there's not any other questions, right about the end of the hour, so the timing is perfect. So again, appreciate everyone still out there, and if you want a copy of the material for this webinar, please contact your Forberg sales representative, and we look forward to helping you guys all out in the future. Have a great rest of your day.
Thanks, everyone.